Hello, today we are going to talk about GAMS software or modeling system. GAMS is basically a general algebraic modeling system. We are going to employ GAMS for optimization problems. First, I'll try to introduce the basics of GAMS with an example, and then we'll just go in detail in the details of GAMS in further treatment for reservoir sizing and reservoir operation. So, GAMS. Now, you're supposed to get software from the GAMS website, where www.gams.com. And once you start the GAMS program, you have GAMS IDE. GAMS is General Algebraic Modeling System, and IDE is Integrated Development Environment. So you would have such an interface here. So the first thing you have to do is you have to set working directory advisably. In many softwares, it's basically important to have a working directory prior. So you have to go to File here, and then Project, New Project. Then we are going to create a folder. In my case, I'm going to create in the desktop. I'm going to create a folder by the name Giga. So I've just created a folder. Within that folder, I'm going to create a file name. Let me just call this file name Gigre. So Gigre is the name of the project which I'm about to create. So when I say open, then you can see in the title bar, it says GAMS IDE, and then it shows the path, the folder Giga, and within that Giga folder, you have gigre.gpr. The GPR extension would tell you GAMS project. Now we are ready to write the code in GAMS. So all you have to do is just click on File again, and then this time New. Now this is the interface in which we are about to write the code. So before starting writing the code, you can see here an extension untitled._1.gms. So this is where you're going to place the code. So let's first talk about the code itself, the basics of the GAMS code. Now, the basics of the GAMS code involves first declaration of variables, then declaration of equations, definition of equations, definition of model, then solving the model, and writing the output. Now, I'm going to demonstrate this with the wastewater treatment example, which is the linear programming problem, which we have solved earlier. So first comes declaration of variables, the variables which we are going to use. So the variables which we are about to use shall include, among others, the decision variables and the name of the objective function itself also. Just to remind you the basics of the equations in the wastewater treatment plant problem. Remember, that was the equation. Maximize x naught. Here I'm just writing it like maximize z is equal to 5x1 minus x2. Then you have those set of equations for the constraints, as you can see at the bottom of the slide. So using this set of equations, first we are going to declare x1 and x2 are the variables, decision variables, and then it's by virtue of x1 and x2, when they vary, z does vary. So x1, x2, and z are variables, And we also know that when they vary, so does Z here. By Z here, not to confuse, we can just call this like Z here. So you can clearly see here, in this set of examples, you can clearly see here the value of the objective function. So x1 and x2, they are variables, and Z is also the variable. So in naming variables in GAMS, you can use letters, you can use numbers and underscores. But it should always start with an alphabet. It cannot start with a number. It cannot start with an underscore. It can only contain any one of those combinations, but should always start with an alphabet. So naming x1 is possible, x2 possible, or ABC possible, but you cannot say 1x because it has started with a number. It should start with an alphabet. So this is also true when you label equations. Name of equations should always proceed with an alphabet. Now, so the first thing that comes to is declaration of variables. Since x1 and x2 are specifically positive variables because of the non-negativity constraints. So we are going to specifically declare them separately as positive variables. Even though x1, by virtue of the value change in x1 and x2, so that z will change. But x1 and x2 should always be non-negative, but z could be negative. So we separately declare z and x1 and x2. Every statement in GAMS should end up with semicolon. So we say variables, and then z, and then semicolon. Then positive variables separately, x1, x2, semicolon. Now, let's give names for each one of those equations. Let's give a name, let's say for the first equation, the objective function, let me just call it obj. Let me call the first constraint C1, second constraint C2, third constraint C3. So we just gave names. So in the declaration of equations, we're going to use those names. So we say equations obj, comma, C1, comma, C2, comma, C3. Each one of those names of the equations have to be separated by commas. Similarly, like in declaration of variables, they need to be separated by commas. Of course, you could have listed downward, in which case you don't need to have commas. But just to know the basics, here we are just writing it like with commas. At the end of the statement, everything has to be ended up with semicolon. Now, we have just finished declaration of variables and declaration of equations. Next comes definition of equations. Each one of the equations which we have declared needs to be defined now. So first we write the name of the equation and then followed by two periods, two dots. And then we just write the equation. Now, before writing the equation, it's important to clarify certain symbols. If you want to write equality or is equal to in GAMS, all you have to do at the bottom of the slide, you can see is equal to E is equal to. If you want to write greater than or equal to, then you have to write is equal to G is equal to. If you want to write less than or equal to, then we say is equal to L is equal to. Now we can clearly write each of the equations separately. So we say obj Z is equal to E is equal to 5 times we have to explicitly write the multiplication sign, x1 minus x2. Since we have now finished with the first equation, we put semicolon. Don't forget to put the semicolon. Then C1, the next equation, and then 2 periods. 2 times x1 minus x2 is equal to L is equal to 10, which means less than or equal to 10. Then we finish with semicolon. Then the second constraint, C2 dot dot 2 periods, 0.4 times x1 plus 0.8 times x2 is equal to L is equal to 4. Semicolon. Last constraint C3, 2 periods, 2 times x1 minus x2 is equal to G is equal to 0. Semicolons. Mind you, GAMS is not case sensitive. So small g is the same as capital G. Now we have just finished definition of equations. Next comes definition of model. Here what you are required to do is you have to write model and then give the name of the model and then backslash. If all of the equations go into one model, then we say backslash all and then close using backslash and then semicolon. That's definition of the model. Next is solve. Solve would have 6 items. First, the keyword solve. Then the name of the model, which has been specified earlier. Then the keyword using. Then, depending on the context of the set of equations, if it can be solved using linear programming, LP. If it's going to be solved using nonlinear programming, NLP. Then, would you like to maximize or minimize? In this specific example, we want to maximize. So, maximizing Z. Don't forget to write Z here. That's what's going to be maximized. And then semicolon. Then the final thing is writing the outputs. In a very simplistic form, you can write the outputs on the screen. So you can use display, the keyword display, then x1.l, comma, x2.l, comma, z.l. By L, we mean level. Now, let's try to run this code. First, I'm about to copy only the code from here for simplicity, or you can just directly type onto the GAMS code displaying screen. So I just copied that. I'm about to run the model now. To run the model, you may have a couple of options. You may either use run GAMS, the red button. You can see in the standard toolbar, the red button. Or you may just click on File, and then there is Run. Or you may use F9. But for simplicity, I just press the red button here, Run GAMS. When you run it, now you can see optimal solution found somewhere. In the no active process window, you can see optimal solution found. Don't close this window. If you don't have any red colored line, then obviously GAMS has properly been executed. To find the results, you have to go to a window which is formed in untitled_1.lst. So there you have the last line which reads display. Then click on the plus button, expand that, click on any one of the variables, let's say on x1. Then on the right side, you can see the values now. Variable of x1.l is 6, x2.l is 2, z.l is 28. That is in agreement with what we have achieved using the graphical method, and then later using solver, and then using primal simplex. So this is the force option which we have used now, giving the same result. Now, as you have seen here with the display statement, it clearly runs and then gives the result on the screen. If you make any mistake somewhere, yeah, let's say if I just wrote instead of, let's say, x in the display statement, if I say x1.l, x2.l, and if I say x3, which has not been specified earlier, mind you, and then let me run it again. If you run, then you say there is some error. You can clearly see here there is the red line. So don't panic. All you have to do is just double click on the red lines, and then it will just clearly show where you have possibly made the mistake. X3 has not been defined before in the decision variables. So you have to check that and then change it to X1. Yeah, it so runs now. Yeah, or if you made the mistake of, let's say, missing the multiplication sign somewhere here, 5 times x1, and then if you run it, then obviously you do have mistakes, red lines. So click on any one of them, then it will show you where possibly you have made the mistake, possibly. So preferably, you have to click on the first red line here, then it will just bring you to where the possible mistake could be. So you put the multiplication sign, you run it, now it works, basically. But as you can see from here, the result is displayed on the screen. What if you want to have the result in the folder? Then in that case, all you have to do is you don't have to have this last line of display. This line you don't need. Display statement. Delete that. And instead of that, you're going to put these lines. So first you have to say, instead of the line that starts with display, then you have to write first 5, the keyword 5, and then you have to put a pointer, kind of like a nickname, and then the name of the 5 should follow in backslash. And then you put. It's like write in Fortran. It's like see out in C++ programming. Yeah. So you put, and then we write the pointer which we have specified above. In my case, ans. Then put, then in quotation mark, then we are going to put a string. Whatever you write here, including spaces, would be printed as it is. Then comma, put 2 backslash. Put backslash means new line. Put 2 backslash means 2 new lines. Then put goods. In the file created, it will just type goods. And then put x1.l. Mind you, we haven't put x1.l in quotations. We just put it as it is, because it's the result of the computation. Next we will comma, next we put backslash, that means new line. Put west, so the west is in quotation, mind you, so it will be printed as it is. Then put x2.l, so that's not in quotation, mind, don't put that in quotation, but will just give the result for x2. Put backslash, new line. Put optimum value in quotation, it will print as it is, comma, put z.l. Put 2 backslash, but that's not important as such. So I'm going to copy that segment here, then Control C, and then I'm going to paste at the end of the last line of the code which we wanted to modify. So now you can run it. Now it has run. But this time around, we don't have display in the LST file. optimal solution is found in the no active process window. You can see that. You can find the result. If you just go through the lines somewhere around the bottom, you can see the line that starts with put 5. Double click on it. So it will bring results of optimization of treatment plant, goods 6 west to optimum value 28. So now we are able to use GAMS. If you wish, you can save the code if you wish. So you can just go to save as usual, and then just give it any name you wish. Let's say if I can just give it Bethlehem. You don't need to give an extension. It will just save it by itself. Yeah. So if you want to modify the code next time, then you can use those codes which have been saved in the folder which you have created. Now we are able to use GAMS. We'll talk about details of GAMS later in more detailed form. Here you do have GAMS. It would, in a more detailed form, would contain sets. A set would tell you an index. Suppose you want to declare variables of, let's say, 1,000 variables. So are you going to put them like x1, x2, x3, That's going to be cumbersome. So instead of declaring each one of those variables separately, you could have used sets. And then you can say sets I \1 up to 1 times 1,000 \. So that would tell later when we declare the variable, the value of I goes from 1 to 1,000. It's the same like index. Yeah. And then we talk about data of 3 types: scalar, 0-dimensional, parameter, 1-dimensional, table, multi-dimensional. For example, if you want to specify capacity of reservoir, of single reservoir, it's just one number, 0-dimensional. If you want to specify time series, let's say of flow, it's 1-dimensional, obviously. If you are going to specify area, elevation, volume curve, that is multi-dimensional. So you need to use tables. So we'll come back to this discussion later. So now let's go to reservoir sizing first. Now, in deciding size of reservoirs, as you know, reservoirs are important for balancing inflows and outflows. So the inflow sequence is assumed to repeat. One of the methods which we use for deciding reservoir sizing, specifically the active storage part, could be ripple mass diagram or sequent peak algorithms, or a more complex method and very commonly used is optimization algorithms. So we want to decide the active storage capacity. In the ripple mass diagram, we are going to plot the cumulative inflows and the cumulative demands. So graphically, we are going to estimate the size of the reservoir. But mind you, the inflow time series you have should be long enough to estimate the capacity of the reservoir. One. Secondly, it should contain the critical periods, lean seasons, specifically drought periods, and fat seasons, flood periods. So these periods are very much critical, and the flow should be long enough. The decay should be long enough to estimate the capacity of the reservoir. Even then, it's a usual practice to have the inflow to be assumed to be to repeat itself, so that to create a very long time series to take care of critical periods that happen during at the borders, at the end of the period, at the end of the time span. Now, in the ripple mass diagram, if you plot the cumulative inflows and superimpose on it the cumulative demand, then the difference between the peaks and the troughs should form the capacities, and the maximum deviations between the peaks and the troughs. So the cumulative demands being plotted as tangent lines on top of the cumulative inflows would form different capacity requirements, and the maximum of which should form the active storage capacity requirement. This you know it from your undergraduate studies. So here you do have time series of inflows, and then the third column would tell you the cumulatives. The fourth column is the demand. Then the fifth column would tell you the cumulative demands, and then the sixth is just a continuation of the time period actually. So we are just looking for the difference between the cumulative inflows and cumulative demands. So the maximum difference would form the capacity of the reservoir actually. Now, this you know it clearly from your undergraduate studies. The other one is sequent peak method. In the sequent peak method, mind you, from mass balance equation, we typically write storage at time t plus 1 is equal to storage at time t plus inflow at time t minus release at time t, or demand at time t. That's with respect to what is stored. But when you specify this equation in terms of the capacities, by the storage we mean how much water has been stored. By the capacity we mean how much water could be stored. By ST we mean how much has been stored. By KT we mean how much more could be stored. That's the capacity. Not the storage, but the capacity. So when you try to write the capacity in time t is the capacity in the previous period plus the release minus the inflow. Basically, when you release much water from the reservoir, you are creating more room, more storage space. When inflow goes into the reservoir, it would decrease the additional capacity, the possible capacity for additional inflows. So that's why KT is equal to RT minus QT plus KT minus 1. If it is positive, if it is negative, then you have to specify 0. So theoretically, when the reservoir is full, then KT is 0. Yeah. So now we can use for the same data which we have used before, we can use the sequent peak algorithm using that set of equations. So you do have the period in the first column, you do have the inflow, the demand in the next column, second column, then you do have the inflow in the third column. So KT minus 1, we just put 0, which means we are assuming the reservoir to be full when we start with the analysis. So RT minus QT plus KT minus 1. So basically it's negative. When it's negative, put 0, it says. So we put 0. So the value of KT in October is the value of KT minus 1 in November. So in November, the capacity in the previous period is the capacity from October. So you put that. So RT minus QT plus KT minus 1 is still negative, so you put 0. So keep on putting that for the subsequent periods. So if you go to the line that starts on April, 9.25 minus 8, that is like 1.25. When you just round it off, it's 1.3. For May, 9.25, demand, inflow is 3. And then capacity from the previous month is 1.3. So 9.25 minus 3 plus 1.25 shall give us 7.5. So if you keep on doing similarly, you can find the maximum capacity in September to be 120.5. Now you can minimize the capacity K. The algorithm would look like minimize the capacity subject to the mass balance equation, and the storage at any time has to be less than or equal to the capacity, and the release at any time has to be greater than or equal to the yield. So we are going to solve this set of equations. We can use this using Excel. I'll just demonstrate this using Excel first, and then I'll come back to the how we can do this equation using GAMS. So I'll just demonstrate that using a set of equations in GAMS. I'm about to demonstrate using this Excel template, which at the Ministry of Water Resources a couple of years ago. Columbia experts from Columbia University were using this Excel template for demonstration of reservoir capacity, for yield, and for a number of other tasks. So I found this easier to demonstrate. So we can easily go through those Excel sheets accompanied with the PDF files. Then you can just go through line by line, and then you can see how we can employ Excel for the purpose of capacity determination. So I'm about to start with the first Excel sheet here, exercise 1, task 1, 2. So I'm going to use the corresponding Excel file, PDF file here. As you might remember, first, just flow duration curve. That's not important for capacity determination, just to get you accustomed to what is in the Excel files. So it says in step number 1, you have to type count inflow in cell B2. So we are going to write in cell B2 here is equal to count in bracket inflow, and then close the bracket. Mind you, that range has been named inflow, obviously. So it's 480. And then we are going to write, next it says, step number 2, then you have to write equal to rank D2, comma, inflow. In cell E2 it says. So in cell E2, we are going to write rank, then open the bracket, D2, comma, inflow, close the bracket, then enter. Now you can populate this. Just double click here. Now we have populated, given the rank. Next we are going to write the exceedance probabilities in cell F2, E2 over n plus 1. So exceedance probabilities we are about to write E2 over, in bracket, I prefer to put that, n plus 1. Obviously, you can see the n would tell you the count. That cell has been named n, it looks like. So enter you put, and then populate that. Double click, and then we have just populated it. And now you are able to graph. Mind you, there is a macro behind this Excel worksheet. In certain cases, it may not load. That means you have to first enable the macros. To enable the macros, all you have to do is just go to File here, and then here options, and then here you do have trust center, then you do have trust center settings, then macro settings. So it says disable. Yeah, just for the time being, you have to enable all macros, but after you have finished your task, you can disable it back. Yeah, before you start the job, otherwise it may not load because in Windows 8 and Windows 10, it will just high security there, so it will just protect your machine. So graph flow duration curve here, it says. Just click on it. Now it's able to plot the flow duration curve. So we just finished this PDF now. So I just move to the next Excel sheet here, PDF file, and continue on the same Excel sheet properly. So to size the reservoir. So we want to size the reservoir. So all you have to do is just in cell G2, you're going to write S initial plus D2 minus D right. So in cell G2, S initial plus D2 minus D right. By D right, we mean the demand. S initial capacity, plus inflow minus demand. We just finished. Next, we have to use in cell G3, we are going to write conditional statement. If G2 is greater than or equal to 0, then put G2 plus D3 minus D right, otherwise D3 minus D right. If G2, open bracket, if G2 is greater than or equal to 0, then put G2 plus inflow minus D right. Otherwise, it's D3 minus D right. Yeah. So the statement would read, if G2 is greater than or equal to 0, then G2 plus D3. Otherwise, D3 minus D right. So we say enter, then you have to populate that. So we just finished now the storage. What's next? We are going to put here step number 3. We're going to use solver. Now, before we use the solver, we have to put here in cell B6, we have to write minimum, mean ST. In cell B6, mean ST is equal to the minimum storage. And then in cell B7, we have to write maximum storage. And then we are asked to put large enough value in cell B5. In cell B5, we are going to write 2000 instead of 1500. So we are going to replace that by a larger number, 2000 now. Next, we are going to use solver. Solver is basically an add-in in Excel. To use add-ins, all you have to do is go to File again, Options, or in certain Excel versions, it might be Excel options. Click on it. Then go to add-ins. While here, click on solver add-in. Then you have to click on go. check the box alongside solver add in. Then you have to say OK. Then you can find the solver in data. Then there is solver here. Now, while here, we want to set the objective function. So the objective function, say target cell or set objective, click on the red button here, and then click storage, B7. So we're going to use set target cell or set objective. Okay, we want to minimize that. We want to minimize that. You don't have the option of maximizing, minimizing. We want to minimize the capacity, the minimum capacity, by changing variable cells. Here we have no idea about the initial storage. We just set it to be 2000. So we want to keep on changing it, the initial storage. Initial storage. And then we are about to set constraints. So these constraints could be the initial storage has to be obviously less than or equal to the capacity, and the data storage, the minimum storage has to be more than or equal to the data storage. So these are the two constraints which we are going to set. So we say add, then we click on the red button here, then as initial here has to be less than or equal to, that's the default, less than or equal to the capacity, which is B7 here. Then we say add, then as mean, which is B6 here, has to be greater than or equal to, actually. Mean res, which is B4, data storage. So the minimum storage has to be more than or equal to data storage, actually. So we just finished. So we have just finished the set of equations. Yeah. So we are about to run the model now. So you can just say solve here. Of course, you could have changed this to simplex. Just this nonlinear could cater for both nonlinear and nonlinear options, but in this specific example, I'm just going to keep it as nonlinear, because some of the equations have those possibilities to be nonlinear. So I'm going to solve it now. So we just finished. So solver has found a solution. So would you like to keep the solution? Okay, we say. So we have just found the capacity to be 3568. Yeah. So that is the capacity of the dam. Now let's proceed to the yield. The third exercise 1, task 3. Create yield reliability curve, it says. So all you have to do is you have going to write initial H2. You're going to type if G2 is greater than mean res 1, otherwise 0. Here, initial H2 is equal to if G2 is greater than or equal to 0, so we're going to write if it is greater than the, sorry, not 0, if it's greater than the dead storage, 1, otherwise 0. Dead storage means mean res, which is B4 here. Then comma 1, otherwise 0, which means if the storage level is more than the dead storage, then you can release water, otherwise you cannot do that. Then populate it. Now we have just populated. Next, we are going to estimate the reliability, which is summation of demand met. How many times have you achieved? How are you able to release water? The ones. You are going to sum that and then divide by the number of total number, which is 480. So we are going to do that here. Is equal to sum in bracket demand met, close bracket. So that would sum colon H or demand met. And then you have to divide this by N. Then this should give you the reliability, right? So the reliability of this reservoir to supply a demand of 155 is 100%. If you make it 145, that's still 100%. 150, keep on changing the demand, 100%. 155, 100%. But only when you make it 160, it keeps on reducing 94% reliability. When you make it 170, 84, it keeps on decreasing, as you can see. Now, if you want to see how the reliability changes as you keep on changing the demand, now we can just click on the generate reliability table here on this tab. So it has just created yield versus reliability. So minimum demands are guaranteed to be 100% reliable. But the minute it increases above 155, then the reliability becomes lower than 100%. So the maximum yield which you can obtain from the dam is 155. So here we talk about basically here we talk about maximizing the yield, but for a given capacity. Earlier, when we were determining the capacity, we were talking about minimizing the capacity for a given demand or for a given yield. Yeah. So as you can see here in the title, minimum capacity given yield. So we were solving this set of equations, which is minimum capacity given the yield. Later we talk about maximum yield given capacity, the reverse. Yeah. So participants, you're advised to go through the rest of the Excel sheets and the corresponding PDF files here. So I'll just come back to the PowerPoint again. So we want to decide the capacity using this set of equations, but this time we are going to use GAMS now. So here is the code we are about to use. The GAMS code for the capacity. So here, maybe for clarity, I'm going to copy this thing in Word so you can clearly see what I'm talking about. Just for clarity, I'm copying, nothing more. Now, here, it all starts with sets here. Sets. Sets, T, that's the name of the set. Time or month is just a description. And then the set goes from 1 to 15. Yeah, 1 to 15. And then parameter. There are 3 different types of data: scalar, parameter, and tables. Scalars are 0-dimensional. Parameters are 1-dimensional. It's just one column or row vector. But here, you may see here the T here is the index actually. So the 1, 2, 3 up to 15, they are the indexes. The actual flows are 5, 7, 8, 4, 3, it's so continuous. So you need to define that within backslash and then make sure you close it again by backslash, and you need to add your semicolons here. Next, we are going to define the capacity. Sorry, the yield rather. The capacity, we want to get it. So that's a scalar, just one quantity, scalar y, that's the name, it's just a comment, and then backslash 5. Next, variables, capacity, we don't know the capacity. That's capacity. Positive variables again, yeah. There are a set of positive variables, ST here It's not just one variable, but 15 variables. Then spill T, 15 variables. Next, we are going to define equations, set of equations actually. Q bar T and cap T. Q bar T would tell you there are 15 set of equations corresponding to the water balance. Cap T would tell you the capacity. 15. As you can see in the set of equations here, the water balance or mass balance equation here made for every period, time period. And then the storage has to be less than or equal to K here. Yeah? So here, instead of writing ST plus 1 is equal to ST plus QT minus RT, we're going to use ST plus 1 is equal to ST plus QT minus yield minus spill T. So here we are saying release is equal to yield plus spill. By virtue of this definition, release equal to yield plus spill, we are saying since the yield from the reservoir is fixed to be 5 here, and since the spill is positive, obviously release is always greater than or equal to the yield, because release equal to yield plus spill, a positive variable. So instead of writing the equation as, I'll come back to this discussion later, but here I'm talking about this part of the equation, the right side of the mass balance equation, ST plus QT minus RT. So instead of writing ST plus QT minus RT, we are writing ST plus QT minus yield minus spill. So you can see it here, ST plus QT minus spill T minus Y. Yeah. So instead of writing the release directly, we are just putting release equals spill plus Y. Since Y is 5 and spill is positive, so release is definitely more than or equal to the yield. So we don't need to specify the third constraint, which specifies RT should be greater than or equal to Y. The other thing is, let's say if you just look at the mass balance equation. So storage in February, that's storage in the second month, is equal to storage in the first month plus inflow in the first month minus release in the first month. If you want to find storage in the third month, it's equal to storage in the second month plus inflow in the second month minus release in the second month. But what about if you reach the end of the time period you have? In my specific example, here, the time span is up to 15 periods. So you cannot talk about 16th time period. So when you are at this 15th, so storage at 15th plus inflow at 15th minus release at 15th, it's going to be, literally, it's going to be storage at the 16th time period, but we don't have 16th time period. So it should look back to the first time step when it is outside the time range. So we are going to write, instead of capital T plus 1, we are going to put here 1. You can clearly see here T plus 1 is equal to 1, it says. Now to write this thing in GAMS, all you have to do is you are going to use $sign. So this would tell you ST plus 1 is like an if clause. When you can write ST plus 1 such that ordinate T less than 15. If the value of T is less than 15, you can use ST plus 1. But if the value of T is equal to 15, then you have to use S1. Because when it is 15, then ST plus 1 is going to be S16, which is non-existent. So to contain for this cyclical property, we are going to use this if conditional statement, ordinate of t. When it's less than 15, ST plus 1. When it is equal to 15, then we say S1. Yeah, so we have just written here the mass balance equation, actually. Next, the next set of equation is about the capacity. The storage has to be less than or equal to what? The capacity. So we have just written the second constraint, and we said the third constraint is not important. It's already implicitly contained in the first mass balance equation. Now we have just finished, and then model we say, just give name of model. For example, I can just call the name of the model to be Ahmed. So model Ahmed \O, and then solve. The name of the model you have to write again, Ahmed, using linear programming LP, minimizing K. And then you have to give file, then name of pointer, let's say res. And then here you have to write also the value of, and then here you have to write name of the file. Huh? So you can write whatever name you have. So I can say here, yeah, minimum capacity, that's okay, min k.txt. So put results, and then ultimately it's going to form here using loop statement. It's going to write for every time. It's going to write the storage, the spill, the demand, the yield, and then here it's going to write the capacity already. The put k.l is going to specify the capacity. So if I may copy, Control C, and then create a new space to write the code. So here is the code now. I'm about to run this. So run it. Now it has run. Obviously, we have put file here. Double click on it. And then here it shows the capacity of the dam to be 14. The yield is 5. And then these are the corresponding values for inflow, for storage, release, and the corresponding yields. Yeah. So this would tell you the capacity of the dam now. Now, how about if you do have evaporation? Now you have to make a little bit modification on the when there is evaporation, we have to make a little bit modification on the mass balance equation. So ST plus 1 is equal to ST plus QT minus RT minus loss from reservoir in terms of volumetric units. So if you just plot from your area elevation volume curve from your surveying at the reservoir area, so you do have area versus storage. If you put the dead storage, you know the area at the dead storage level and the volume at the dead storage level, you know the total storage and the corresponding area at the full supply level. Yeah. So you can just come up with a slope for a linear representation of that line, AA. And then you have the intercept at the dead storage point. So this line would specify the area in terms of the volume. So that should give you the average area corresponding to the average storage. So this average area times the depth of evaporation should give you volume of evaporation. So this average storage, which is ST plus 1 over 2 times the slope of the line of the plot of storage versus area, is AA, and the intercept is A naught. So if we expand that, then you can find this equation now. Now you can specify here 0.5 times AA times depth of evaporation ET in different periods times storage at time t plus 0.5 times AA ET ST plus 1 plus A naught ET. Let's represent 0.5 AA ET by AT, small at. And let's specify A naught ET by BT. So you have AT ST plus AT ST plus 1 plus BT. Now if you substitute this equation instead of LT, then that should give you this equation now. Now rearranging terms, then you just end up with this set of equations. So the capacity determination set of equations, the only change now we can see is in the mass balance equation now. So the new equation would look like this in the presence of evaporation. Now, so far we are talking about finding the minimum capacity given the yield. Now we are about to talk maximum yield given the capacity. Maximum yield given the capacity. Now, the only difference in determination of the yield would be only the objective function. It's the same set of equations as you can see it here. The only thing we have changed is instead of minimum capacity, here we say maximum yield. So you can see here we said minimize K. But here we say maximize Y. That's the only difference. So we are going to use this set of equations just for clarification and demonstration purpose. I'm going to copy this thing into this set of files here. Yeah, now I can easily tell what is what. Now sets T goes from 1 to 9. So you have your inflows that goes from 1 to 9 as the parameter from your data. And then that is closed by the semicolon here. The capacity is given to be here 8 variables, Y, yield, positive variable, storage at time t, set of variables, and then RT, excess storage, excess release. When you are writing the variables downward, you don't need to have the commas, but make sure you put your semicolons there. Equations, there are 3 set of equations. First one is about mass balance. Second one is about the release has to be greater than or equal to the yield. Third one is about the capacity, where the storage at any time should be less than or equal to the capacity. Yeah. So the first one is the mass balance. This would tell you if storage at time t plus 1, if ordinate of t is less than 9, because you have got 9 periods in the inflow time series, as you can see. If it is less than 9, then use st plus 1. Otherwise, if it's equal to 9, then you have to use s1. Then obviously is equal to then storage at time t plus qt minus release at time t. Then second equation is release has to be greater than or equal to y. The third equation is storage at time t has to be less than or equal to the capacity. So we are just using this set of equations here. Then we just give a name for our model here. Yeah, let me just call the model Hyatt, for example. I can just call it Hyatt. Then backslash. Then solve Hyatt. It has to be the same name, huh? Using linear programming, maximizing y. If you want to write comments in the GAMS, then you have to use asterisk and then the comment, but that's not important. Then file, spill, you can say answer if you want, and then the name of the file. And then this is a pointer, has to be the same. And then you are going to write here, these are just comments which you can omit if you wish. Yeah. So that's it. So put K, mind you, here there is no dot L because K is already given. But why dot L? Why is not known? And then here, I could just print this whole thing in quotation as it is, and then it will look for every value of Q, for every value of S, for every value of release, and for every value of yield here. So we're going to copy that, and then let's form a new space for adding the code. Make sure you are in the GMS file. Otherwise, while being in the TXT, then it doesn't work. So I'm here now. I'm about to run it. Now it has run already. Now click on the put file here, double click here. Then it will tell you here for a capacity of 8, the yield is 3.6. Yeah, so we have just solved the yield for a capacity of 8, right? So this is how we can determine the capacity of reservoirs, the capacity and the yield of reservoirs, basically. Next time, we'll talk about reservoir operation. So thank you for now.